Hi, my name is Matheus Bernadelli de Moraes, and I'll be presenting our work, Effects of the Random Forest Hyperparameters in Surrogate Models for Multi-Objective Combinatorial Optimization, a case study using MOID RFTS. First of all, what's multi-objective optimization? It's the idea of optimizing multiple conflicting objective functions simultaneously. In some problems, the objective function evaluations are expensive. They require a considerable amount of computational effort. In this type of problem, using surrogate models is an interesting approach. Surrogate models are approximation functions that try to predict the objective function values without the requirement of expensive evaluations. Using surrogate models may reduce the computational effort and also increase the exploration of the search space. Here's the formulation of a multi-objective optimization problem. The idea is to minimize or maximize a set of objective functions all at the same time. There are the decision vectors, the x with an arrow above. Each decision vector contains n decision variables, and the problem may be subject to equality or inequality constraints that composes the feasible region, represented here by the omega symbol. Recently, random forests have been investigated as an approximation function technique. Random forest is an ensemble of decision trees where each decision tree makes its own prediction of the objective function values of an unevaluated individual. Random forest is an average resulting over these k individual predictions. Random forests have shown to be a low cost but high precision approximation function technique. However, random forests have several hyperparameters that must be defined before the prediction process. To illustrate this idea, let's suppose we have a regional dataset with measured data. We want to use this original dataset to train each one of the decision trees of the random forest. To do that, we have to build a randomly sampled training set for each decision tree. Like this one here. We have the number of randomly sampled decision variables, the number of randomly sampled samples. We can decide if the bootstrap is on. If it's on, we can select each sample more than once. There are the number of trees that the random forests have, the minimum number of samples required to split a node, the minimum number of samples to be at leaf node, and tree depth. In our research, we want to investigate the effects of these hyperparameters on the prediction process of the random forest. To do that, first, we try different combinations of hyperparameter values using grid search and the mean absolute error as a prediction metric. So investigate the performance of the random forests separately from the optimization procedures. Then we perform optimization using the best and worst configurations on optimization problems using a random forest assisted evolutionary algorithm called MOID RFTS. We use the inverted generational distance IgD as the optimization metric, and we compare the results with other state-of-the-art evolutionary methods. As one of our main contributions, we identified that the minimum number of samples to be at leaf node is the most important hyperparameter. As we can see here, if we choose the highest possible value, doesn't matter the values of the other decision variables. We will always get the worst results. And the second most important hyperparameter is the number of samples. These two hyperparameters must be defined carefully. Here, this table shows the wins, draws, and losses when we compare MOID RFTS with the best hyperparameter combination to other two evolutionary methods, MOID and MOID NFTS, and also the same algorithm, MOID RFTS, but with the worst hyperparameter combination. We can see that MOID had 1 win, 3 draws, and 14 losses. MOID NFTS had 2 wins, 5 draws, and 11 losses. And the Same algorithm, but with the worst hyperparameter combination, had 1 win, 80 draws, and 9 losses. So, as the main conclusions, we identified that the number of samples and the minimum number of samples to be at the leaf node are the two most important hyperparameters. And the evidence suggests that the random forest becomes less sensible to changes in the hyperparameter values when the number of objectives increases. As future research, we want to train the random forest with fewer data and consider many objective problems containing more than 4 objective functions. Here is our sponsors. Thank you very much.